So let us say, for example, I have a Boolean function f of x comma y comma z, okay, and this could be anything. I want to look at what happens to f bar of x comma y comma z. What happens when I complement that function itself, right? So effectively it's like this, right? If you look at it from a hardware perspective, I have a black box that implements the function that takes three inputs x, y, z, that implements the function f, and then I am going to pass this through an inverter, and I want to ask what is this. So out here you get f and here you get f bar of x comma y comma z, whatever the function is, right? A trivial example of this is what we had seen earlier, which is basically the and the NAND gates, right? So if I take an AND gate, I get f equal to a and b, and then I pass it through an inverter, I get the a NAND b, that is a and b whole bar. And we want to know, is there an alternate representation of this? So there was an alternate representation. We'll come back to that in some time. Okay. So this is a very interesting question that we want to deal with, and of course it turns out that the AND and OR operations are very fundamental operations. So we will not look at anything very complicated at present. I will start with a very simple example. F of x comma y is equal to x and y, okay, and I want to ask what is f bar of x comma y, which is nothing but x and y whole bar, right, which by the way also can be written as x y apostrophe, right? In this is what you will see in the textbooks, right? So to understand this thing, this statement, right, we can go back a little bit and see what is, what happens in terms of just a logical statement, okay? So I am going to look at a logical statement to analyze this. Okay, so let's say there is a box, okay, there's a box that I don't know what is there. There are a bunch of, there are n balls in this, and there are, all of them happen to be white balls, okay. So I could now make a statement about this box containing balls, right? Every ball in the box is white. Okay, now what is the negation of this statement, right? What is the complement of this statement, right? So every ball in this box is white, okay. What does it take in order to negate this statement, right? So for example, I could have the following situation, okay, n balls, right? I'm just considering 9 balls. I could have just one of them being black, right? In which case clearly that statement does not hold, because every ball in that box is not white, right? Likewise, I could have 2 balls, I could have 3 balls, I could have 4, 5, 6, I could have every single ball being black, right? I could have, I think I said white. So I could have 1 ball being black, 2 balls being black, 3, 4, and every single ball being black, right? And any of these cases, right? So if I look at this, right, this is the case of 3 balls being black, right? Here I am talking of just 1 ball being black, okay? Now likewise I can have every single ball, right? Or maybe 4 balls, 5 balls, whatever. But if I were to complement this, right, and ask what is the complement of this statement, right? The complement could come due to many different cases, right? It could come because one ball is black, 2 balls are black, 10 balls are black, all the balls are black, or any number, right? Any number is of them can be black other than the case of 0 where everything is white. Okay, so already what we see is very clear that in order to complement this situation, in some sense we see that there are many different conditions and any one of them has to hold for us to negate that statement. That is, this or this or this has to hold for us to negate that statement, right? So essentially, if I were to complement this statement S bar is every ball in the box is not white. Sorry. Okay, every ball is not white. And how can that happen? Like I said, it can happen with any single ball being black, any one, any two, any three, and so on, right? There are many cases. So therefore, if I were to represent each ball, okay, with a Boolean variable x, the ith ball is represented by the Boolean variable xi, which is 1 if it is white, 0 if it is black, right? Now the statement S, for the statement S to be true, I need x1 to be white and x2 to be white and x3 to be white all the way to xn to be white. Okay, and now if I take x bar, I am going to say x1, x2, x3, xn and complement that statement, right? It's very evident, like I told you, that it need not be that every single ball has to be black for that statement to be negated. No, any one ball can be black and that statement will be negated. And therefore, intuitively you already see that this could be negated through x1 bar, right? That is, if the ball is black, right, then x1 will be 0, which means x1 bar will be 1. That means x1 bar represents the case when the ball is black. It could be x1 bar, or the second ball is black, or the third one is black, or any one of them, xn bar, happens to be black, right? Now the beauty with the OR gate, right, on the right hand side is that for example, x1 and x2 could both be black, right, and the others could all be white, right, in which case this will simply reduce to x1 bar plus x2 bar, right, or any combination. But effectively any one of these being white is sufficient for me to negate this statement and get the complement of that. So therefore, this statement essentially is what is known as DeMorgan's laws. Right, which basically says x into y whole bar is equal to, I don't need the parenthesis here, x bar or y bar. Okay, likewise right? I could also have the counterpart, right? X or y whole bar is equal to x bar into y bar, right? So this happens to be the case when I am looking at just two variables, but the example that I showed you with the balls is actually that of n Boolean variables, x1 to xn, right? So therefore, what we can do now is we should try and also algebraically prove if these statements are true or not. Okay, so let us take this example, x into y whole bar equals x bar or y bar. Okay, now what we can do is we can look at x and y. Let this be z equal to x and y. So then what we are saying is z into z bar happens to be 0, right? Z into and z bar we know is 0, right, for any Boolean variable, and therefore if I can show that the x dot y whole bar, right, that is z bar, if z bar happen to be x bar plus y bar, right, then I would have proved that x and y whole bar is equal to x bar plus y bar, right. So this is a slightly indirect way of showing it. We are trying to show this, we have to prove this. I mean, this is given for any z. And what if x or if z bar happens to be x bar plus y bar, right, then I, you know, I have to show, right, I have to prove that z in and x bar plus y bar is equal to 0. Then I would have shown that z bar is equal to x bar plus y bar, right. So let's go ahead and look at that. Z is equal to x and y, okay, and I'm going to do and x bar plus y bar, right. This is equal to x and y into x bar and x bar plus x y bar. Now it is essentially commutative, right? It does not matter in which order I evaluate the ands and ors, right? I have to I just have to evaluate each of these terms. In each of these terms, it does not matter in which order I evaluate the ands and ors. So I will rewrite this as y and x bar, okay, or x and y bar, okay, and therefore this is very trivial for us to show that this is equal to x and x bar, right. X and x bar, this we know is 0, likewise this is also 0, implies this is equal to 0 or 0, which is 0, right, and therefore I have been able to show that hence proved. I have been able to show that this the z bar is equal to x bar plus y bar, right, hence prove that x y whole bar is equal to x bar plus y bar, okay. So likewise the other dual of the DeMorgan's laws is x plus y whole bar is equal to x bar and y bar. Okay. So what we can do here is, again, let's say z is equal to x plus y. Okay. What do I want to now show? I want to show that z and z bar is equal to 0, right? Or you want to try something different, you can also show that z or z bar equal to 1. Okay, if this happens to be true, right? Of course, this is true, right? Like in the previous case, for all z, Boolean z, this is true. Z or z bar is 1. Now, if z bar equal to x bar and y bar, right? Then I basically can show that this, I can, if this happens to be true, then I can say that the DeMorgan's laws has been proved, right? So therefore, let us look at that. Z plus z bar, right? If z bar equal to x bar and y bar, right, is equal to z and z or z bar is x plus y plus x bar y bar. Okay, I need to show, to prove that equal to 1. Okay, so let's look at the LHS. X plus y plus x bar y bar. Okay, so we will write this as x plus x bar y bar, okay, plus y. Again, commutative law, I'll write it in the way that I want suitably here. Then we also saw this distributive law. We saw that x plus a plus bc was equal to a plus b and b, a or c, right? Here a is equal to x, b is equal to x bar, c is equal to y bar. Therefore, implies x plus x bar y bar is nothing but x plus x bar into yes, x plus x bar into x plus y bar, right? So yes, okay, so therefore x into x bar y bar, so this is nothing but x into x plus x bar into x plus y bar, okay, and this is therefore equal to x plus x bar, we know that is equal to 1, and therefore this is equal to x plus y bar, okay. And what else do we have now? So this one on the right hand side, okay, implies x plus x bar y bar plus y, okay, is equal to x plus y bar plus y, right? And y or y bar is equal to x plus, yeah, you get x plus y plus y or y bar, right? And this is not, we know that this is equal to 1 and this is therefore equal to x or 1, which implies this is equal to 1, right? And therefore, which is nothing but equal to the RHS. Remember, this is what we wanted to prove. Okay, we wanted to prove this, which is equal to the RHS, and hence right? So with this, you will see that we are able to prove a number of theorems, right, and simplify numerous expressions that we get in in Boolean algebra. Okay.